Welcome to this explainer. Today, we're diving right into the mechanics of IP spoofing. But more importantly, exactly how network defenders stop it dead in its tracks. We're putting on our analyst hats for this one, going way beyond the basic textbook definitions. We're going to look at how attackers manipulate the fundamental rules of the internet, why some of these attacks are just absolutely devastating, and the real-world toolkit industry practitioners use to lock down their environments. To ground our understanding right out of the gate, think of IP spoofing exactly like putting a fake return address on a physical piece of mail. You can write literally whatever you want in the top left corner of an envelope and drop it in a mailbox. And amazingly, the Postal Service, they'll still deliver it. But if the recipient decides to write back, well, that reply is going straight to the fake address, not to you. And that is exactly how IP spoofing behaves on a network. An attacker sends a packet with a forged source IP. The packet reaches its target, sure, but any replies go out into the void. Or, worse, to the poor innocent party whose address was forged in the first place. So here is our roadmap for today. We'll start with the fake return address, look at the trust flaw in IP, dive into the threat of reflection attacks, explain why web browsing fails, and finally unpack an analyst's mitigation toolkit. Let's kick things off with Section 1, the trust flaw in IP. You see, a router has one massive fundamental flaw. It blindly trusts the destination IP without ever verifying the sender. Remember, the Internet Protocol was designed decades ago, basically in a utopian era where trust between networks was just assumed. In normal communication, say your laptop at 192.168.1.10 sends traffic to a web server, the server knows exactly who sent it. But when an attacker injects a spoofed packet, maybe claiming to be from Google's 8.8.8.8, the router's only job is to look at the destination, let's say 10.10.10.100, and push it forward. It doesn't pause for a second to ask if the packet genuinely originated from 8.8.8.8. Because of this historical design choice, malicious systems can easily inject packets with fake or random source IPs right into the network. Which brings us to Section 2, why web browsing fails. Now, a lot of people wonder why attackers don't use this trick to invisibly surf the web. Well, web browsing relies on TCP, and TCP strictly requires a two-way conversation to establish a connection. You know it, it's the classic TCP three-way handshake. The client sends a SYN, the server replies with a SYN-ACK, and the client confirms with an ACK. But think about what happens with a spoofed IP. The attacker sends that initial SYN, forging the source IP to look like a victim. The server receives it and happily replies with a SYN-ACK. But where does that reply go? It goes to the spoofed victim. The attacker never gets the server's response. Without that response, they can't complete the handshake, and the connection just completely drops. As analysts, we know that modern randomized sequence numbers make blind session hijacking practically impossible today, effectively rendering IP spoofing totally useless for typical two-way web browsing. Moving right along to Section 3, the threat, reflection attacks. If they can't browse the web, what's the point, right? Well, attackers leverage this fundamental flaw to create massive DDoS reflection or amplification attacks. This is absolutely the most common and devastating use of IP spoofing today. Instead of attacking a victim directly, the attacker sends a spoofed request to an innocent third party, like a public DNS server. First, the attacker sends a tiny request, but they forge the source IP to be the victim's address. Next, the DNS server processes that request, totally unaware it was spoofed, and prepares a massive response. Finally, the DNS server sends that massive response to what it thinks is the requester, the victim. Now, imagine an attacker doing this not with one DNS server, but with thousands simultaneously. They literally turn these innocent servers into a giant fire hose aimed directly at the victim. As an analyst, when you see a sudden, massive influx of DNS or NTP traffic hitting your edge, you aren't looking at a direct attack. You are looking at the fatal consequences of IP spoofing amplification. Now for the really good stuff, Section 4, an analyst's mitigation toolkit. The absolute industry gold standard here is ingress filtering, formerly recommended as Best Current Practice 3.8, or RFC 2827. This stops spoofed packets right at the network edge. Here is how an analyst actually implements this. They configure the router to ask one simple critical question when a packet arrives. Should this source IP be arriving on this specific interface? For example, if an interface is connected to a customer subnet of 192.168.10.0 and a packet arrives on that interface claiming to be from 1.1.1.1, the router immediately knows it's a forgery. It simply drops the packet. No questions asked. Widespread adoption of ingress filtering by internet service providers is literally the single most effective way to kill reflection attacks at their source. To automate this logic, analysts deploy a highly effective feature called uRPF, or Unicast Reverse Path Forwarding. Common on enterprise gear from Cisco, Juniper, Arista, and Nokia, uRPF essentially uses the router's own routing table as a security tool. When a packet arrives, the router looks at the source IP and asks, hey, if I wanted to send traffic back to this source, would I use the exact same interface it just arrived on? If the routing math says the return path doesn't match the inbound interface, the router assumes the IP is spoofed and drops the packet. It's just an incredibly smart, dynamic way to enforce interface discipline. Furthermore, analysts program their edge firewalls with strict anti-spoofing rules. A core part of an analyst's job is recognizing traffic that is structurally impossible in a legitimate scenario. For instance, traffic claiming to be from private IP ranges like the 10. Network or the 192.168 network should never, ever arrive inbound from the public internet. The same goes for bogan networks like the local loopback 127 address block. If a packet arrives from the outside internet claiming a source IP from one of these reserved internal ranges, it is undeniably a spoofed packet trying to bypass simple IP-based trust rules. The firewall is programmed to drop these silently and immediately. To complete the defensive posture, modern networks rely on a layered approach. We've talked a lot about filtering incoming traffic, but responsible networks also utilize egress filtering on outbound traffic to ensure their own compromised internal machines can't send spoofed traffic out to the internet. Next, because we obviously can't control the whole internet, analysts absorb reflection attacks using massive cloud-based DDoS protection services like Cloudflare, Akamai, or AWS Shield. These providers can identify spoofed traffic patterns and scrub malicious traffic before it ever hits the enterprise edge. And most importantly, modern security architectures never trust an IP address alone. Even if an attacker successfully spoofs an allowed IP using robust authentication like TLS certificates, SAML, and multi-factor authentication, ensures that the attack still completely fails. Let's wrap this up with Section 5, a CCNA-style summary. This cheat sheet perfectly synthesizes our explainer today. Let's do a rapid-fire checklist. What is IP spoofing? It's forging the source IP. Most common use? DDoS reflection attacks. Why does when browsing fail? Because TCP responses go to the spoofed IP, breaking the handshake. Best mitigation? Ingress filtering, specifically BCP 38. And the OSI layer involved? That would be layer 3. As an analyst, your primary job is to enforce trust, not just assume it. Remember our analogy from the beginning. Anyone can write a fake return address on an envelope, and the architecture of the internet basically allows this at a foundational level. So I'll leave you with this critical thought to evaluate regarding your own infrastructure as you design your defense in depth. Ask yourself, is your network blindly trusting the return address?